Okay. Um, in this lecture, I'm going to introduce the concept of reactions on surfaces, and in doing so, I'm going to review catalysis. So, the content in this lecture is based on the Nobel lecture by Gerhard Ertl, who won the Nobel Prize in 2007 for his work on surface science and catalysis. You can find the content for this lecture in an article that's published in Angewandte Chemie International Edition, which is linked here. Okay, so basically what we're going to do is continue our discussion of reactions at the molecular level on what's going on. We're going to do this in the context of a catalytic reaction. So a chemical reaction involves the breaking of existing chemical bonds and the formation of new bonds. And this procedure, this breaking and forming of bonds, this involves the transfer of energy. In fact, it involves a transfer of significant amounts of energy. So the transfer of energy. The energy that is transferred from the potential energy that's stored within the existing bonds. And part of that energy may be transferred to the formation of new bonds. And some of that energy may be transferred elsewhere, for example, released as heat. So stored within the original chemical bonds. For example, some of this energy may be released as heat. And that would happen in an exothermic reaction. We also know that for the reaction to occur, there must be enough energy available or supplied to overcome the activation energy. And we also know that the rate of reaction is going to be proportional to the exponential of the activation energy divided by RT. R is the gas constant and T is the absolute temperature. Hence, the rate can be increased by either decreasing the activation energy or increasing the temperature. So the first one of these is where a catalyst comes into play. So the catalyst, the function of the catalyst is going to be to decrease the activation energy. The way it does this is by forming an alternate route from reactants to products. This involves the formation of different intermediate species, and ideally, all of these species are lower energy intermediate species than would result in the analogous homogeneous reaction. So a catalyst decreases activation energy by forming or creating, I'm going to say enabling an alternate reaction pathway. This new pathway results in the formation of new intermediate species and is typically a lower energy pathway than the homogeneous reaction. We'll say, actually, let's say the uncatalyzed reaction. So for example, here we have a kind of just an arbitrary sketch of this. So we have our energy axis here, and then we're basically showing here on the x-axis different locations along the reaction pathway. In the absence of a catalyst, we have one activation barrier, and in the presence of the catalyst, we have two. However, both of those activation barriers are lower than the barrier in the absence of the catalyst. So what's going on here in the presence of a catalyst is new intermediate species are forming. Those are involved in reactions, at least two reactions going on here, but the reactions happen at a lower energy, a lower activation energy than the pathway without the catalyst. So the catalyst is providing a lower energy route from reactants to products, and doing so it's forming more intermediate species, but these intermediate species are allowed to form because they're lower in energy. They're more stable. So what's going on here in catalysis? The reaction happens on the surface, on the catalyst surface. It typically happens in several steps. In one step, reactant molecules from the gas phase adsorb to the catalyst surface. When we say adsorption, what we mean is formation of a bond between the reactant molecule and the surface. And this bond can be either chemical or physical. Chemical bond is formed when the orbitals of the molecule and the surface mix and form new orbitals. So there's going to be new bonding orbitals formed and new anti-bonding orbitals formed based on the original orbitals. A physical bond is more like a dispersive interaction, like a Leonard-Jones type interaction, where the electronic structure of the molecule and the surface are perturbed, but no new orbitals are formed. When a molecule adsorbs to the surface, it can be either physical or chemical. Once adsorbed, the reactant molecules can fully or partially decompose on the surface. So for example, a simple example would be if we bind molecular nitrogen, then it could dissociate to two nitrogen atoms on the surface. This is an example of a situation where the adsorbed species are much more stable than the gas phase species. It is much more energetically preferable to have oxygen atoms adsorbed to a surface than it is to have oxygen atoms in the gas phase. Once these atoms and molecules are formed, once they're on the surface, they can react with each other. So an example of this would be carbon monoxide bound to the surface, reacting with oxygen bound to the surface to form carbon dioxide. So in this case, an oxygen atom reacted with a carbon monoxide molecule to form CO2. Another thing that would happen would be that the product molecules would desorb from the catalyst surface. Desorption is essentially the reverse of adsorption. And an example of this would be our CO2 molecule that's adsorbed to the surface, leaving the surface and going into the gas phase. So over here I might have my CO2 molecule, and now I'm a gas phase molecule no longer attached to the surface. So the surface of the catalyst is one of the biggest things it does, or the key things that it does, is it binds these intermediate species and stabilizes them. The reason that it does this is because when the surface is created, essentially what we're doing is cleaving bonds between surface atoms. So those surface atoms used to be nestled within a larger, maybe bulk structure of the material, but we create a surface and we basically sever those bonds. So that means that the atoms in the surface are chemically unsaturated due to the creation of the surface. They the atoms on the surface are hence hungry to form bonds. So they're going to bind with these different reactant and product species and intermediate species because they want to form bonds. So the creation of the surface is largely what makes catalysis possible. So the catalyst really binds with atoms and molecules because the atoms in the surface are chemically unsaturated due to creation of the surface. They're hungry to form new bonds. So one important application of catalysis is the ammonia synthesis reaction. So that's where molecular nitrogen reacts with molecular hydrogen to form ammonia. The reason this is important, in the first part of the 20th century, the world was facing starvation due to an increasing population and depletion of fertilizers. So there was a need to create a process that would more fastly produce ammonia. And this was done by a variety of contributors. The most well-known are Haber and Bosch, who designed the Haber-Bosch process to create ammonia from the nitrogen in air. So this right here is a diagram showing the relationship between the changing population and the amount of global ammonia production. So the ammonia that's being produced is being used for food. So the more ammonia we have, the more food we can grow, and that's related to the overall population growth. What the Haber-Bosch process does, it uses a catalyst comprised of iron. These catalysts, industrial ammonia synthesis catalysts, they actually comprise nanometer-sized particles of iron with surface areas of around 20 meters squared per gram. So you think about a gram, it's, typical rule of thumb is something that weighs a gram is an M&M. So for every M&M, there is 20 meters squared of catalyst surface area available. Under reaction conditions, the iron doesn't remain metallic on its own. It would actually be present as an oxide. But the iron oxide can be reduced to metallic iron by incorporating potassium oxide. So the working catalyst includes potassium oxide, and the potassium oxide doesn't participate necessarily in the bond breaking and forming, but it does maintain the metallic electronic state of the iron. So now we have these iron nanoparticles, and they're being maintained. Their metallic identity is being maintained by this potassium oxide. Another issue with the Haber-Bosch process is that it occurs at high temperature and pressure, and typically at high temperature and pressure, metallic nanoparticles are going to want to sinter, which means they're going to want to combine with each other. This is prevented by attaching them to a supporting material, specifically an alumina support is used. So these little nanoparticles are grafted along the alumina support where they bind pretty strongly, and this prevents them from combining with each other. So this is part of what maintains the large surface areas. The main utility of the iron catalyst is to dissociate molecular nitrogen. So molecular nitrogen is pretty difficult that's a pretty difficult thing to do. So that's a triple bond. It's a very strong bond, so it's not something that you can just do with heat. So you need something else. And so a catalyst surface will stabilize atomic oxygen. It likes to bind with atomic oxygen, and we can show this energetically. These are all diagrams of molecular nitrogen absorbing to the catalyst and then dissociating. So here we have molecular nitrogen gas. This right here is the catalyst surface. We'll say the metal catalyst surface. So all the spheres, all the orange spheres are iron atoms. This is adsorbed N2. So here what we are modeling or looking at is a reaction between gas phase N2 adsorbing with the surface to form adsorbed N2. These right here are the energies involved in the process. So this is an energy axis. This axis right here is the distance from the surface. If we, and here we have our 1D representation of this, and here we have our 2D representation of this. If we go through and label what's going on here, right here, that is going to be our N2 gas. This right here is going to be my adsorbed N2. And this right here is going to be 2 adsorbed nitrogen atoms. So this right here is going to be the energy associated with adsorption, and this right here is going to be the energy associated with surface dissociation, or dissociation of N2 on the surface. All right, what am I? One more thing. This right here, this is going to be a transition state, or approximately a transition state. So that it's going to give us approximately the transition state to that is in between adsorbed or this 2 adsorbed nitrogen atoms and adsorbed nitrogen, molecular nitrogen. So if we wanted to know what the activation energy of that process is, we could, of the dissociation process, we could, it's going to be about this amount of energy. Okay, here we have our, this right here is our 2D representation, where we see our 2 adsorbed atoms are about right there. The minimum energy pathway between reactants to products is about right here. We see the adsorbed molecule here. The transition state to dissociation is right there. This is a contour plot. Okay, and so this diagram is illustrating that it is energetically feasible to dissociate molecular nitrogen on the surface. So if we compare the gas phase energy of molecular nitrogen to the energy of 2 adsorbed nitrogen atoms on the surface, we see that it is downhill. And the next diagram shows that it is much more energetically to do this on the catalyst than it is to do it in the gas phase. So here we have energies in kilojoules per mole of gas phase versus catalyzed reaction pathways. So we said that one of the key things the catalyst is doing is dissociating the nitrogen molecule, also the hydrogen molecule. So this right here, I'm going to draw it around here so I don't draw over top of anything. This is the energy of nitrogen, atomic nitrogen gas plus 3 atoms of hydrogen gas versus adsorbed, we'll say adsorbed nitrogen plus 3 adsorbed hydrogen. And the difference is 1400 kilojoules per mole. So it's 1400 kilojoules per mole more stable for these species to be on the catalyst surface than in the gas phase. So these species are very unstable in the gas phase, and they are quite stable relatively on the catalyst surface. This here, this piece of the diagram, this is our gas phase pathway. So basically the hardest part is getting or forming the atoms, the nitrogen and hydrogen atoms, and then once we have those, we can start creating the the ammonia molecule, and the overall process is just slightly downhill in energy. This right here is the catalyzed pathway, or the catalytic pathway. As you can see, the catalytic pathway is significantly lower in energy than the gas phase pathway. So the catalyst is providing a lower energy pathway from reactants to products. That's the catalyst job. It's making this reaction possible. Whereas in the gas phase, you'd have to put in 1,400 kilojoules per mole of energy to get that to happen. It's a lot of energy. That is like 30 times the amount of energy per mole to vaporize water. Okay, so another thing we can do from this diagram, from this catalytic pathway, is write the reaction mechanism. So basically what I'm going to do that is go step by step. So this is step 1. Actually, let me do that in a different color. So here's step 1, this is step 2, this is step 3, etc. So I'm going to go and write the different steps for this reaction. I'm going to break some of them apart. This step here is actually concerted. We have nitrogen and hydrogen adsorbing simultaneously. I'm going to break those up. I like to write elementary processes in my diagram, my reaction mechanism, so I'm going to break all that up. So if I extract out all of the elementary processes from this diagram, I get, I'm going to use this color, nitrogen adsorption. It's where molecular nitrogen gas adsorbs to the surface. I also have hydrogen adsorption. I now have to dissociate nitrogen and hydrogen into adsorbed atoms. Then I'm going to start reacting these species. So N add adsorbed nitrogen reacts with adsorbed hydrogen to form adsorbed NH. NH reacts with hydrogen to form NH2. NH2 reacts with adsorbed hydrogen to form NH3. Now we have our ammonia. Now we just need that to desorb. So NH3 add desorbs, forming our product, NH3 gas. And of course, some of these reactions are going to happen more than once to create a cycle. So this reaction is going to happen, 3 times for every 1 time that this reaction happens. That's fine. I'm just going to write them as single processes. And if we were wanting to write the rates of these species, we would know, for example, that this process is happening 3 times faster than this one under our steady state. Okay, so in this notation, the one thing to keep in mind when I write add with a species, that means that the atom or molecule, I guess I could say species, is adsorbed to the catalyst. This means it has formed a bond with the catalyst. So for us to be able to capture that species, it needs to break the bond with the catalyst surface, meaning it needs to desorb and go back into the gas phase.